Tonight, we're looking at our closest neighbour, Venus. A rocky world dominated by swirling clouds, once thought of as Earth's twin.
But in fact, these planets could hardly be more different. One is a cradle for life. The other, an inferno, scorched by acid rain.
Why have these close neighbours become so different? And can Venus teach us anything about the Earth's past, or indeed, its future?
It's a great time to view Venus from here in Britain at the moment. It sits high in the evening sky and is visible soon after sunset. It's also the brightest object in the night sky apart from the moon, so it's pretty hard to miss.
Even though it's easy to spot, Venus's enigmatic nature and its inhospitable surface means that it still has plenty of mysteries intact. So we've come here to the Mullard Space Science Laboratory, part of University College London, where specialists have built instruments to help explore this most fascinating of worlds.
They form part of the most advanced spacecraft to ever visit Venus, the European Space Agency's Venus Express. Its 8-year mission has just come to an end, and we'll be finding out what it's discovered.
Also coming up, we'll be looking into a new picture of the violent origins of both Earth and Venus.
Lucy Green will be looking at how and why Venus has taken such a different course to Earth.
What was it that made Venus's atmosphere so searingly hot and spotted with acid?
And we'll reveal what a marvellous treat it is to have Venus in our night sky. Venus is the second planet from the Sun, a rocky world like our own, and the similarities don't end there. The Earth and Venus are almost exactly the same size, though Earth's about 600 kilometres thicker around the waist.
The planets seem to be built in the same way, with a rocky outer core, and they've got very similar masses too.
Both have a thick atmosphere, though Venus's is mostly made of carbon dioxide. But despite this difference in composition, there's plenty that's familiar. There are clouds and there's weather. In fact, it's the layer of clouds surrounding the planet that help make Venus so bright in the night sky, because they're highly reflective.
It orbits the Sun once every 224 days, but it rotates very slowly, so a day on Venus is longer than its year. And Venus's rotation is one of the great mysteries of the solar system, because it rotates clockwise. That's in the opposite direction to the Earth. All the planets and most of the moons rotate anti-clockwise, but we'll get more on this later.
Now, with all of these similarities, it's no surprise that people used to think of Venus as a nice place. They used to believe there was a tropical forest hidden underneath those clouds. When the first space probes arrived, they've revealed something rather different.
On the 15th of December 1970, after 15 failed missions, Russia's Venera 7 landed successfully on Venus. What it and subsequent landers found was many people's image of hell. They revealed that the pressure on the surface was greater than being at the bottom of an ocean. Temperatures were 462 degrees Celsius, and the atmosphere contained toxic clouds of sulfuric acid. Most probes only survived for around an hour, but their findings beg an important question. Why is it that a planet that's so similar in some respects to our own can be so vastly different in others? And in particular, what was it that made Venus's atmosphere so searingly hot and spotted with acid? We think 4 billion years ago, Venus was a lot more like Earth. There's evidence that it once supported bodies of liquid water, possibly even oceans. But at that time, it was the Sun that was very different. It was less powerful than it is today, and only around 70% as bright. But gradually, the energy of our sun began to increase, and any bodies of liquid water on Venus evaporated, driving water vapour into its atmosphere. It's thought that this was the start of a series of events that created cataclysmic change. To see what we think happened, I'm going to try and recreate them in the lab. The first culprit is not traditionally linked with intense heat, it's water.
Although we normally associate water in the Earth's atmosphere with cold days, we think of rain and we think of clouds, water vapour, which is essentially water in its gas phase, just a few molecules held together, this can trap heat and it acts like a blanket around the Earth.
From clouds we can see to invisible molecules of water vapour, water is all around us. Our atmosphere contains nearly 13 trillion tonnes of H2O.
And because there's so much water in our atmosphere, it's actually water here on Earth that's our most important greenhouse gas. And the extra water vapour that was added into Venus's atmosphere had a potent greenhouse effect.
Even more devastating is what we think happened to that water as it rose to the top of Venus's atmosphere. Under the full intensity of the sun's ultraviolet light, the water molecules were split into hydrogen and oxygen.
Much of the hydrogen escaped into space, but the oxygen, which is a highly reactive element, combined with other molecules. One was carbon, and it formed carbon dioxide.
Of course, carbon dioxide is the archetypal greenhouse gas, and you can see just how much it absorbs heat by comparing a simple flask of air with one that I'm filling with carbon dioxide, made by mixing just a few simple ingredients.
And what we need now is a heat source to represent the sun, and for that I've got some lamps. And lastly, a bit of patience. We have left these flasks for over half an hour now, and we've been tracking the temperature of the gases inside. And in fact, I've got a plot here to show you what's been happening. The orange curve shows the temperature of the carbon dioxide, and it has become almost 1.5 degrees warmer than the air alone. So the carbon dioxide has been trapping the heat more effectively. And in fact, that rise in temperature happened very quickly. And I think that really shows just how good the carbon dioxide is as a greenhouse gas.
It's the extra heat that carbon dioxide traps that on a planetary scale drove a vicious chain reaction. The more Venus heated, the more greenhouse gases were created. But it wasn't just carbon that the oxygen combined with, it also bound to sulfur, creating sulfur dioxide, which in turn formed droplets of viciously corrosive sulfuric acid. So Venus's hellish atmosphere is all the result of a runaway greenhouse effect. And it raises a disturbing question. Is there a risk that this kind of extreme climate change could ever happen here? Hugo Lambert is a climate change expert.
Well, let's think about the future then, because I wanted to ask you, is there any chance at all that we might have a runaway greenhouse effect on the Earth and end up similar to Venus?
We certainly don't see it as being a realistic endpoint of any of the kind of man-made climate change scenarios that we talk about for the next few hundred years. We can foresee a future, maybe in 2100, where the Earth's surface is perhaps 10 degrees Celsius warmer than it is now. But in order to get a runaway greenhouse effect, then we would need to get nearer a mean temperature of perhaps 60 or 70 degrees Celsius. Then you would have so much water in the atmosphere that all of the infrared radiation emerging from the Earth's surface would be absorbed by the water vapour.
And this is exactly what we think played out on Venus. But how certain are we that we've got this story right?
I think the key word you've used is story. It's a hypothesis for explaining how Venus works. It fits in nicely with what we understand about the Earth, what we understand about Mars, what we understand about Venus. But we don't have any proof. We can't look at the history of Venus. We can't trace that backwards in time. But what we could imagine doing is catching other planets around other stars that are like Venus. So during their early days, we would expect to see, for example, an atmosphere which is full of steam.
Well, this is a really nice idea. So you would use the broad number of exoplanets discovered around other stars and hope to catch them at different evolutionary points.
That's absolutely right, yes.
I presume also it matters what kind of star you're orbiting around as well, because each class of star will be emitting different amount of radiation at different wavelengths.
That's absolutely right. For example, if it was a very, very red star, a cool star, then the ice at the surface would no longer reflect radiation that efficiently, because ice is actually quite good at absorbing infrared radiation. It would absorb the radiation from that star in a way that it wouldn't absorb radiation from our sun, because sunlight bounces off snow and ice and is reflected back into space quite efficiently.
So it's much more complex than just looking for the perfect region around a star where you've got the right temperature. I used to think that Venus was on the inner part of the sun's habitable zone, but actually it turned out to be a planet that couldn't be more different to what we have here on Earth.
Well, I certainly wouldn't want to live there.
It's tempting to think of Venus's thick atmosphere as nothing more than an impediment to studying the planet below, but it's much more than that. It's fascinating in its own right, and it's here that Europe has been leading the way with a probe called Venus Express that's just spent 8 years orbiting the planet. Following its launch in November 2005, Venus Express took 5 months to reach its target. Peering through Venus's clouds is difficult, but the spacecraft was armed with instruments designed to study the atmosphere and any magnetic field that exists. Maggie found out what the mission revealed by talking to Colin Wilson.
Venus Express has been gathering data for 8 years. What have we discovered?
So after previous missions which had focused on the surface, Venus Express is very much focused on the atmosphere of Venus. And we've been able to focus on the atmosphere of Venus at all altitudes, from the lowest levels right near the surface, right up to the upper levels. We can illustrate this by looking at a picture of Venus. So, for example, this is what you would see if you approached Venus in a spaceship. So what can you see?
It looks a bit dull, I must say.
Yeah.
Bit
Well,
billiard ball-like.
Billiard ball-like is right. Dull is probably not the word. It's very, very bright, because the clouds are very reflective.
So what are
reflective
these
from the
clouds made of?
So on Earth, of course, we have clouds made mostly of water. On Venus, they're made mostly of sulfuric acid. So it's because there's so little to see on normal images of Venus, visible light images of Venus, that normally we go to other wavelengths to find out interesting things. So, for example, if you want to see features in the clouds, you can go to the UV, and you can see very much more the cloud features. You can see the clouds moving about, swirling about the planet.
One of the first things these images revealed was what a constantly changing world Venus is. That is dramatically illustrated by what happens in the polar regions.
The poles of Venus have these enormous vortex features. So the reason you get a vortex in any atmosphere, any planetary atmosphere where the planet's rotating, is very much like what happens when you pull the plug out of a sink. So in planetary atmospheres, if the equator regions are heated more by the sun, then that heats the air up, it travels towards the pole, and then it swirls down into this vortex before getting sucked down.
That sounds impressive.
I'll show you some, yes. So this shows you clouds swirling around the vortex. And then when it jumps, that's going to the next orbit, which is 24 hours later. And it really changes shape quite dramatically from day to day.
Venus's atmosphere isn't just changing on a short daily timescale. It's also changing from year to year.
After 8 years of observations, we can really look to see how things have changed over that timescale. And we're still compiling that. But we've seen, for example, that the mean wind speed at the cloud tops of Venus has increased by 100 kilometers an hour over the course of the mission. So at the beginning, the mean wind speed was about 300 kilometers an hour, and then it's gone up to about 400 kilometers an hour by the end of the mission.
So over a period of 8 years?
Yeah.
So do you think that's sort of a continuing trend?
But we think we might be seeing a really long, slow oscillation of the atmospheric state, perhaps a bit like El Nino on Earth, where you have year-to-year changes in how the circulation of the atmosphere works.
So are there other dynamic changes occurring in the atmosphere of Venus?
In addition to the wind changes, we've also seen changes in the chemistry. The main variable constituent in the Venus upper atmosphere is sulfur dioxide. Now, sulfur dioxide is really interesting because on Earth, the only naturally occurring source of sulfur dioxide is volcanic emission.
Interesting.
Volcanoes. So, now we know Venus is covered in volcanoes. We know this from radar missions, which mapped Venus in the 80s and 90s, but no one knows whether they're active or not. And so, what we've seen with Venus Express is tenfold changes in how much sulfur dioxide is in the upper atmosphere. Now, it could be that this is due to circulation changes, but a much more exciting possibility is that there's changes in the amount of volcanic activity and eruptions and so on.
And there is other tantalising evidence that volcanoes could still be erupting today.
We imaged the same region repeatedly throughout the course of this 8-year mission.
Yes.
And, for example, here's one region, and you see on day one it's sort of tepid, a mere 450 degrees or so. But when we came back a couple of days later, the temperature's gone right up to thousands of degrees.
Yes, so there's a little red hotspot.
A little red hotspot, which shows that the temperature's gone really high. And when we came back a couple of months later, the temperature of that region's gone right back down again. So this suggests a lava flow, which is then cooled off again.
Yes, because it's hard to think of what else could be causing that sort of rising temperature.
That
so
kind
locally.
of, yeah. It's not just a blip in the image, because it's not a sort of round circle. It can't be a cosmic ray or anything like that.
Oh, right, yes.
It can't be a cloud feature. So it's very tempting to think it's active volcanism.
Despite its rural appearance, MSSL is one of the world's leading space science centres. Within these buildings, that used to be potting sheds, critical components for Venus Express were constructed. And right now, instruments for Europe's next generation of space exploration are being worked on. Well, I'm here with Andrew Coates, who's worked on a number of space missions, but is also one of the lead investigators on the Aspera 4, one of the most important instruments on Venus Express. So we've got lots of hardware in front of us. Can you tell me a bit about it?
Yeah, we've got some very interesting instruments here. So this one actually is one of the models for the ExoMars PanCam, which is actually going to Mars in 2018.
So this is a panoramic camera?
That's right, panoramic camera system. So it actually has 3 different cameras in this system. It's one of the most sophisticated cameras ever to be sent to Mars. So our camera system sits on the top of the rover here, and this will actually be looking for signs of life on Mars.
So what else have we got?
The other things which we've got are, for example, here there's the solar wind analyzer for solar orbiter. One of the things which we've developed here over the years is very good measurements of electrons in space. So this is the sort of latest incarnation of that.
So why do you measure electrons in space?
To measure currents and this sort of thing, but also the solar wind is a plasma consisting of ions and electrons, and so the electrons are a very important component of that. So to measure the electron precisely, the blackening that you can see here on these hemispheres, this is a technique which we developed here for making sure that light doesn't get into the detector.
And the ultraviolet photons would actually give you a signal as well?
Yes, that's right, because the detector would respond to those too.
So this is Venus Express now?
Yeah, so for Venus Express, we actually use that blackening technique. And so this is one of the hemispheres which we use to deflect electrons around to actually be measured on the detector inside the instrument. And so this can tell us some fantastic information, for example, about how quickly the atmosphere of Venus is escaping.
Ah, so Venus is losing atmosphere?
It's losing atmosphere, yeah. So Venus lacks a magnetic field. Unlike the Earth, which is protected to some extent by a magnetic field, Venus doesn't have such a thing. And so the solar wind, which is a 1,000,000 ton per second stream of material coming out of the sun all the time, can interact with the atmosphere of Venus and actually pull it away.
It sort of erodes it?
Yeah, that's right. We had a paper this year measuring the amount of escape from Venus, from the top of the atmosphere, and we see about 300 kilograms of the atmosphere per day is actually escaping. Taken over billions of years, this means an awful lot of material has been lost.
So what has surprised you in terms of the results you've got from Aspera 4?
Looking at the composition of the material which is actually escaping from Venus, it actually turns out to be water. The composition is very much like, so you've got twice the amount of hydrogen compared to the amount of oxygen going off. So that's H2O, you know.
Yes,
and so
water,
yeah. And that was a big surprise because, of course, the atmosphere of Venus is basically carbon dioxide, but it shows that water is still being lost from the Venus atmosphere, and so this dehydration is a process which is still going on and has been going on for billions of years.
Well, thank you, Andrew. It's been fascinating seeing the kit and hearing about the data. Thank you very much.
Thank you.
Sometimes astronomy doesn't need expensive equipment or even a dark sky. Venus is beautiful and easy to spot wherever you are.
Apart from the sun, the moon and the odd passing comet, Venus is the brightest object in the night sky. And that means you don't need to go to a dark sky site to be able to see it. In fact, Venus is so bright you can see it during the daytime. This is easiest to do when it's close to the moon, as that gives you something to locate it by. Venus is one of the inner planets, which means that it never wanders that far away from the sun in the sky. And that gives some spectacular opportunities to take photographs of Venus in the early morning or evening twilight, even with something as basic as a camera phone. At present, Venus is easy to see just after sunset above the western horizon. But this is set to change, so now is the time to catch it. Venus is really high up at the moment. You can see it blazing away behind me there, and it's absolutely beautiful to see it in the sky on its own like that. But also being so high up, that places it out of the wobbly bit of the Earth's atmosphere, so if you're an imager, it gives you a clearer, sharper image. Now, as the sky starts to get darker, then we'll start to see the stars behind Venus, and occasionally the planet will move in front of some very familiar objects. It recently passed the Pleiades star cluster and will be passing M35, another star cluster, during the second week in May. As Venus moves around the sun, so it'll change from being an evening object to a morning object, visible just before sunrise. Now, this transition is set to occur this year about mid-August. One of the wonderful treats when viewing Venus is that it shows different phases. Now, on the 6th of June, Venus will reach a point in its orbit which gives us what is known as the greatest eastern elongation. And that's when Venus appears at the maximum distance away from the sun in the evening sky. At about this time, Venus should show a 50% phase. But by far my favourite views of Venus are when it's in a crescent phase, and that's coming later this year. Whether you're a novice or a serious astronomer, Venus has a huge amount on offer. So for how to find it and what else to look out for, here's my guide to this month's night sky. Venus is currently easy to find. Just look towards the western part of the sky in the evening twilight following sunset. It's the bright dot dominating the view. A beautiful crescent moon sits close to Venus on the evening of the 21st. Bright Jupiter can also be seen above and to the left of Venus at the start of May, with the gap closing ahead of a spectacular conjunction set to occur at the end of June. Finally, if you're up in the early hours, look towards the eastern half of the sky. If your sky is nice and dark, you should be able to make out the misty path of the summer Milky Way, now beginning to rise into view.
And now to that question of why Venus has such unusual spin. It seems it might have something to do with how the rocky planets formed in the first place. The story begins with the newly formed Sun surrounded by a disk of material called a protoplanetary disk. You can see such a disk around a nearby young star in this amazing telescope image. The traditional view of how planets form all starts with dust. Tiny particles of carbon and silicon, about a tenth of the size of sand grains. And when these things collide in the disks of material that form around newly formed stars, they can stick together. It's actually the attraction between molecules on their surface that allow these things to grow to form bigger and bigger clumps. And that process works until you get to things the size of pebbles. And after that, you need gravity to take over. And you can build up piles of rubble that go on to gather all the debris around them and form decent-sized planets, eventually grabbing hold of the gas in the disk as well and forming Jupiters and Saturns and Uranuses and Neptunes. The only problem with this picture is that we don't understand how to make rocky planets like Venus and Earth. For that, something more violent is required. The idea is that a series of cataclysmic collisions and mergers created both the Moon and the 4 inner planets. they're the victors of a gravitational struggle that played out between numerous objects, each of them the size of Mars. One of the leading proponents of this theory is Craig Agnall. So I find this stunning. So in the inner region of our solar system, basically where we're standing now, we're talking about what? Tens, maybe 100 moon Mars-sized objects wandering around the inner solar system.
Slamming into each other.
Completely changes how I think of the thing. It's not the quiet, restful place I'd imagined. It's this very violent environment.
That's right. And when these planets start to scatter off of each other, they actually destabilize the whole system in the sense that they all start scattering off of each other.
And we still see the effects of those collisions today.
Certainly. A Mars mass impactor hitting a proto-Earth of about 90% of its current mass can explain the rotation state of the Earth. It can explain why the moon has very little iron in it, and it can explain why the lunar samples that were returned back looked to have been heated to a very high temperature, as this collision would have heated the Earth and the moon to thousands of Kelvin.
What about on the other terrestrial planets? If we look at Mars, if we look at Venus, do we see evidence that they had impacts as well?
Certainly. On Mars, it looks like Mars has a thicker crust on one hemisphere than on the other, and a collision may be responsible for that.
So half of Mars is almost a giant impact basin.
Yes, it's a kind of a crater that's mapped onto a sphere. And for Mercury, we think that the large iron content of Mercury may result from a very large impactor blasting off a mantle. So whereas the Earth experiences a collision with a Mars-sized impactor that helps form the moon, maybe Mercury was a Mars-sized object that experienced a giant impact that had its mantle blown off.
What about Venus? Because Venus has some oddities about it as well.
Well, Venus has a retrograde rotation, and one of the things that giant impacts do is they come in at some sort of random orientation.
And then the impacts flip things one way or the other.
It could be 50% odds that you would have a prograde spin and roughly 50% odds that you would have a retrograde spin if it's acquired through giant impact.
Why did they have such different outcomes? Why did Mercury lose its outer layers and the Earth get a moon and Mars end up 50-50?
The variables are how big was the thing that hit you? When in your history did it happen? How head-on or oblique was the collision? So the difference between the moon forming impact and a disruptive event is roughly a factor of 2 or 3 in the velocity.
So what you're saying is this is just how stuff happens.
That's right. The picture that collisions or giant impacts might be special may come from the specialness of the Earth and thinking that we needed a special impact to form the Earth's moon.
Because we're on this special place that we like very much.
That's right, but collisions just happen. And these collisions can have many outcomes and many expressions in the final characteristics of the planets.
Where are the mysteries left? What can't we explain through this process?
Where the field is moving now is trying to explain the chemical compositions. Where does Earth's water and oceans come from? Why does the Earth have oceans instead of Venus at the moment? Why are the atmospheres different?
How do we make progress there? What sort of data would you need to understand more about Venus?
Sample returns. The sample returns from Apollo kind of illustrate what sample returns can do for you. They tell you, there were 3 theories for the origin of the moon prior to Apollo that they were trying to test, and the answer that comes back from the Apollo data is a 4th theory.
So it's fascinating stuff. Thank you very much. That's it for this month, but when we come back next month, we'll be travelling back to comet Churyumov-Gerasimenko to find out what Rosetta has discovered.
We'll be getting the latest images and getting an update on the Philae lander, lost and sleeping on the comet's surface.
There's already such a wealth of information being returned from this mission that I can't wait to find out what the latest discoveries are.
In the meantime, get outside and get looking up.
Good night.
More heavenly programming coming up here on BBC4. We get the comet's tail tomorrow at 9 as we look over our ancestors' reactions to the bright lights in the sky. And still to come tonight, the thrilling and terrifying story of Russia's cosmonauts. The gun goes off on the space race next.